But to show that Cp minus Cv is equal to R, first of all, let's see what this Cp and Cv and R are. Cp is the principal specific heat at constant pressure, which is defined as the amount of heat released or absorbed at constant pressure. Cv is the principal specific heat at constant volume, defined as the amount of heat released or absorbed at constant volume, and R is the universal gas constant. Then from the first law of thermodynamics, which relates the quantity of heat being equal to the work done plus the internal energy. But this quantity of heat is equal to the number of moles times the specific heat capacity times the change in temperature. Have the first condition that if 1 mole of an ideal gas is subjected to heat at constant volume, not this constant volume, then the quantity of heat will be equal to the specific heat capacity at constant volume times the change in temperature, that is Cv times the change in temperature, and its differential becomes dq equal to Cv dt. Then the first law of thermodynamics becomes Cv dt equal to du, that is the internal energy. Remember, the work done will be equal to 0 because the change in volumes at constant volume, it will be equal to 0. That is V2 minus V1 is equal to 0. Therefore, the work done at constant volume is 0. So the second condition is that if the same quantity of heat, is subjected to 1 mole of an ideal gas, that if the same quantity of heat is subjected to 1 mole of an ideal gas at constant pressure, then the quantity of heat will be equal to Cp, that's the quantity of heat, the heat capacity at constant pressure times the change in temperature. Its differential is dq equal to Cp dt. Then the first law of thermodynamics becomes Cp dt equal to P dV, that's the work done, then plus Cv dt, that's the quantity of heat at constant volume. So we've rewritten the first law of thermodynamics as Cp dt equal to P dV, the work done, plus Cv dt as the heat capacity at constant volume. But P dV, that's the work done, is equal to nR dt. But it is for 1 mole, therefore n is equal to 1. Therefore P dV is equal to R dt. Then we'll substitute back into the first law of thermodynamics, and it will become Cp dt equal to R dt plus Cv dt. Then we will factor out dt into R plus Cv. Then we divide it through by dt by dt. then Cp will be equal to R plus Cv. If we write it, then it will be Cp minus Cv equal to R. And this is the Mayer's equation relating the heat capacities of ideal gases.